everyone, I'm Professor Harrison, and welcome back to our module on probability for finance. Today we're going to be covering joint distributions, marginal distributions, and conditional distributions. Three ideas that are really one idea, looked at from three different angles. We're following Danny, a gambler with a mountain of debt, working his way through a box of mysterious letters addressed to his late father, trying to understand what happened to his family fortune. Today he's trying to figure out whether two problems he's facing, the estate clearing probate and his debt settlement he's going through, could really be treated as separate questions, or whether they're actually the same problem. He opens up another one of those mysterious letters. Think about a coin flip game. You flip two coins at the same time and you're betting on both outcomes. Now, because each coin is fair, you might assume you already know everything there is to know. Each coin lands heads half the time and tails half the time. What else is there? Well, as it turns out, there's quite a lot. Knowing each coin's individual behavior tells you nothing about how they move together. Two fair coins can be completely unrelated to one another, or they can be rigged so that both tend to land at the same way most of the time. The individual behavior looks identical in both cases. The joint behavior is completely different, however. If you're betting on outcomes simultaneously, it's the joint behavior that matters. A joint distribution is what captures that relationship. The joint distribution of two random variables assigns a probability to every possible combination of values those two variables can take at the same time. Let's say you're watching a two-coin game. Call the coins X and Y. Each one lands on heads or tails. The four possible combinations are both have heads, X has heads and Y has tails, or X has tails and Y has heads, and then both tails. The joint distribution puts a probability on each of those in four cells. Suppose the game is slightly rigged. The house runs it so both coins tend to land the same way, probably due to like some magnets or something. The joint probabilities end up like this. Both heads have a probability of 0.4. X heads and Y tails has a probability of 0.1. X tails and Y heads has a probability of 0.1. And both tails has a probability of 0.4. Add those up. 0.4 plus 0.1 plus 0.1 plus 0.4, and you get 1. They have to sum to 1 because those four cells cover every outcome that could possibly occur. That's the normalization requirement we established earlier in the module. Now look at what the table is telling you. The heavy weight sits on the diagonal. Heads, heads, tails, tails. Both coins are individually fair, but they move together when one coin lands heads, the other tends to land heads too. You never see that from looking at either coin on its own. You need the joint table to understand this relationship. So where do the individual probabilities actually come from? If you only watched coin X and ignored coin Y completely, what would you observe? You'd observe that X lands heads with probability of 0.5. That's a fair coin. But where does the number live in the joint table? The marginal distribution of X is what you get when you take the joint table and sum across all the values of Y. For each possible value of X, you add up the joint probabilities over every possible value of Y. So the probability that X equals heads is the joint probability of X being heads and Y heads, plus the joint probability of X being heads and Y tails. That's 0.4 plus 0.1, which ends up being 0.5. The probability that X equals tails is 0.1 plus 0.4, also 0.5. Same calculation for coin Y gives you the same result. Both marginals are 50-50. That's why they're called marginals. They live in the margins of the joint table. They are the row sums and column sums. And here's the thing to hold on to. Once you collapse down to the marginal, you've thrown away the relationship between the two variables. The marginal distribution of X looks exactly the same whether the two coins are correlated or completely independent. Looking at either coin on its own, you can't tell. You need the full joint table to understand what's actually going on. One common question is why would we ever want to use the marginal distribution when the joint ends up containing more information? Well, the answer is it depends on what exactly you're trying to make a decision about. If you're betting on only one of these coins, then the only thing that matters is the marginal distribution. But if you're betting on both of them at the same time, then you need the joint distribution to understand what's possible and what the assigned probabilities to those outcomes actually are. Now suppose you're watching the game and coin X has already landed. It came up heads. You haven't seen coin Y yet. Given what you know, that X was heads, what's the probability distribution for Y? That's the conditional distribution of Y given X equals heads. And you find it by looking at only the row where X equals heads and then rescaling those probabilities so that they sum to 1. The row where X equals heads has two joint probabilities. X heads and Y heads is 0.4, and X heads and Y tails is 0.1. Those two values cover all the scenarios where X already has landed heads. To turn them into a proper conditional distribution, divide each by the total probability that x equals heads, which is the marginal 0.5. So the conditional probability that y equals heads, given that we already know x landed on heads, is 0.4 divided by 0.5, which ends up being 0.8, or 80%. The conditional probability that y equals tails, given x equals heads, is 0.1 divided by 0.5, which ends up being 0.2, or 20%. Now we can check normalization. 0.8 plus 0.2 equals 1. The conditional distribution sums to 1 because we've restricted to a specific scenario, where x was heads, and within that scenario we need to complete the probability distribution. So what does this tell you? Without any information about x, coin y lands heads with a probability of 0.5. But once you know x came up heads, the probability of y also landing heads ends up being 0.8. Conditioning on one outcome completely reshapes the distribution of the other. That's the whole point of the conditional distribution. When two variables are related, knowing one changes what you should expect from the other. The way I keep this straight in my own mind is, the marginal asks, what does y look like in general, without knowing any other information. The conditional, however, says, what does y look like if I restrict my attention to the cases where x took this specific value. And you'll notice that the conditioning formula is exactly what we covered in the earlier video on conditional probability for events. The probability of A given B equals the joint probability divided by the marginal probability of B. That's the same operation here, extended to the full distribution of random variables rather than a single event probability. Danny puts down the letter. He's been treating his two problems as if they live in separate worlds, the estate and his debt settlement. Two things that are either going to work out or they're not on their own. But he's never written down the joint table. The estate has two outcomes. It clears cleanly, or it doesn't. The debt settlement has two outcomes. It goes through or it doesn't. That gives 4 cells. And Danny knows the cells aren't symmetric. His father's estate clearing cleanly and his debt settlement being accepted simultaneously. That's the heads outcome. His father's estate not clearing and his debt not being settled, that's like the tails outcome. And Danny suspects the weight sits on the diagonal, not spread out evenly across all 4. They're not independent problems because the money from one can help with the other. He can sketch the marginals separately. His father's estate clearing, what's that probability on its own? His debt being settled, what's that probability on its own? Those are answerable questions, but the marginals are incomplete. The cells he actually needs to know, the probability that both go wrong at the same time requires the joint table. And then there's the conditional he's been avoiding. What's the probability his debt gets settled when Victor's fund was insolvent at the time of death? That dramatically narrows the picture. He knows that, he just hadn't written it as a conditional distribution before. So that's the joint, marginal, and conditional distributions. The joint distribution captures how two random variables behave together, not just individually. The marginal is what you recover by summing out one variable, but that operation discards the relationship between them. And the conditional is what you get when you fix one variable and ask what the other looks like within that constraint. 3 views of the same table. And which of these perspectives we need to take depends on the question that you're asking.